In 2019, a team pointed Hubble at a faint, half-starved black hole. Weak black holes should not carry thin, fast-spinning disks around them. The physics says that structure needs a black hole feasting hard, not barely eating. Astronomers checked this one anyway, expecting nothing unusual. What came back did not match a single prediction on the books. A galaxy picked for a simple test supermassive black holes sit at the center of nearly every large galaxy in the universe, including the Milky Way. Most of the time, they are not doing much. They only glow brightly when large amounts of gas and dust fall toward them, heating up and lighting up in the process. Astronomers call a black hole active when this feeding is happening, and the brightest feeders can outshine every star in their galaxy combined. Not every black hole gets that kind of meal. Many sit on what scientists call a low luminosity diet, pulling in just a trickle of material instead of a flood. Current models predicted that when a black hole is fed this lightly, the material around it cannot hold together in a flat, organized shape. Instead, it should puff up into a thick, disorganized cloud, something closer to a donut than a plate. A team of astronomers wanted to confirm that prediction using real data, so they picked a spiral galaxy called NGC 3147, located about 130 million light years from Earth, as their test case. It seemed like the perfect galaxy to prove the rule. Its black hole was clearly underfed, which meant the messy donut shape should be easy to spot. What the team actually saw when they aimed one of the most sensitive instruments ever built at that galaxy changed the entire plan. The instrument built to catch faint light, seeing anything clearly, this close to a black hole is extremely difficult. The region right around a black hole gives off very little light compared to the rest of its galaxy, and normal telescopes on the ground cannot separate that faint glow from the blazing light of billions of nearby stars. From Earth, the black hole's signal simply gets buried. Hubble solved that problem with an instrument called the Space Telescope Imaging Spectrograph, or STIS. A spectrograph works by splitting light apart into its individual wavelengths, similar to how a prism splits sunlight into a rainbow. That split reveals details about speed, temperature, and motion that a plain photograph could never show. STIS gave the team enough precision to isolate the small, dim region right around the black hole and block out the overwhelming light of the surrounding galaxy. Astronomer Marco Ciaberge, who worked on the study at the Space Telescope Science Institute, later explained that without Hubble, the discovery would have been impossible, since ground-based telescopes get completely dominated by starlight and lose the faint signal from the black hole's core. With that faint signal finally isolated, the team could see something forming close to the black hole that nobody had planned to find, and it did not match the calm, thick cloud their models had promised. The disk that broke the rule. Instead of a puffed-up, shapeless cloud, Hubble picked up a thin, fast-moving disk of gas wrapped tightly around the black hole. This was not a small detail. A thin disk like this is normally something scientists associate with quasars, the extremely bright, gas-guzzling black holes found at the centers of the most energetic galaxies in the universe. Quasars can outshine entire galaxies because their black holes are feasting on huge amounts of material at once. The black hole in NGC 3147 was doing nothing close to that. It weighed around 250 million times the mass of the Sun, but it was eating so little that it barely qualified as active at all. Lead researcher Stefano Bianchi of Università degli Studi Roma. Trey described the structure plainly, calling it a scaled-down quasar disk, the same basic shape seen in objects that shine 1,000 or even 100,000 times brighter. Finding that exact structure around a black hole, this quiet, made no sense under the models the team had trusted going in. Ari Leor of the Technion Israel Institute of Technology had expected the opposite result entirely. His team chose this galaxy specifically because they thought it was the best possible candidate to confirm that below a certain brightness, a proper accretion disk simply cannot exist. What Hubble showed instead was gas locked into a tight, orderly, spinning ring, moving in a way that could only be explained by a thin disk sitting extremely close to the black hole. The rulebook said this should not be able to happen, and yet there it was, sitting in Hubble's data for anyone to check. Speeds that bend light itself. Once the team confirmed the disk was real, the next question was how fast the material inside it was actually moving. The answer turned out to be almost as strange as the disk's existence in the first place. Gas swirling in that thin ring was clocked at more than 10% of the speed of light, an almost unthinkable speed for anything made of ordinary matter. At speeds like that, strange things start happening to light itself. Gas moving toward Earth on one side of the disk appeared brighter than normal, a phenomenon astronomers call relativistic beaming, where the light gets concentrated and boosted along the direction of motion. On the far side of the disk, where the gas was speeding away from Earth, the opposite happened, and the light dimmed noticeably. The black hole's gravity was also stretching the wavelengths of light coming from deep inside the disk toward the red end of the spectrum. A signature of gravity so strong it takes real effort for light to climb out of it. Bianchi summed up why this mattered so much, saying the team could not make sense of the data without applying both general and special relativity at the same time. Something rarely seen this clearly in visible light. A discovery that started as a simple test of feeding models had turned into a natural laboratory for watching Einstein's century-old equations play out in real time, just a short distance from a black hole that was not supposed to have anything this dramatic going on around it. A correction that did not erase the discovery. Big discoveries like this one almost always face a second round of scrutiny, and this was no exception. The paper describing the disk was published in the monthly notices of the Royal Astronomical Society, and it drew attention from astronomers around the world who wanted to understand how a black hole on such a meager diet could support a structure normally reserved for far hungrier objects. The explanation the team offered was not that the models were completely wrong, but that the transition from a thick, disorganized cloud to a thin, organized disk does not happen at the exact brightness level scientists had assumed. NGC 3147's black hole appeared to sit right at an unusual point in that transition, feeding just enough in just the right way to hold together a disk that should have broken apart under standard predictions. The team hoped to search for similar disks around other quiet black holes to see whether NGC 3147 was a rare exception or an early clue that the old feeding models needed a real update. If you're enjoying this breakdown, hit subscribe so you don't miss where this bracket goes next. That correction did not make the discovery any less important. The disk was still real, the extreme velocities were still real, and the relativistic effects captured by Hubble were still some of the clearest ever recorded in visible light. It simply meant that predicting exactly when a black hole should or should not have this kind of structure around it was far messier than anyone had assumed going into the study. A lesson that would echo through several unrelated black hole mysteries in the years that followed. Why this black hole kept surprising everyone. Every detail of NGC 3147's black hole seemed to argue against the disk existing at all. It was not blasting out huge amounts of energy like a quasar. It was not pulling in massive amounts of gas. By every normal measure, it was one of the least dramatic supermassive black holes astronomers study. A quiet neighbor rather than a cosmic monster tearing through its surroundings. Yet the data kept pointing to the same conclusion no matter how the team checked it. The motion of the gas, the brightening and dimming caused by relativistic beaming, and the stretched wavelengths from gravitational effects all lined up with a thin, fast rotating disk sitting close to the black hole rather than a thick, slow-moving cloud. Chia-Bergen noted that the team had never before seen the combined effects of general and special relativity show up this cleanly in visible light data from any black hole, active or not. That combination of evidence made it difficult to dismiss the finding as noise or a measurement error. Something about this particular black hole in this particular galaxy was allowing a structure to form that theory said should be reserved for far more energetic environments. The team was left with a genuine puzzle rather than a simple confirmation, and that puzzle pushed them to think differently about where the line between a thick cloud and a thin disk actually sits. What astronomers took away from it, the biggest lesson from NGC 3147 was not that Einstein's theories were wrong, since the data actually confirmed them in dramatic detail. The lesson was that the simple rules astronomers use to predict a black hole's surrounding structure based on how brightly it shines are far less reliable than anyone had assumed. A black hole can look calm and undernourished from the outside, while still hosting an extreme, fast spinning structure close to its center. This mattered beyond just one galaxy. Thousands of supermassive black holes across the universe are classified using the same basic brightness-based models that failed to predict what Hubble found in NGC 3147. If one quiet, well-studied black hole could break the pattern this badly, other black holes previously written off as too faint to have anything interesting happening near them might deserve a second look with sharper instruments. The team also gained a genuinely new tool for testing relativity. Finding a natural laboratory where the effects of gravity and extreme speed show up this clearly in ordinary visible light is rare, and it gave researchers a fresh way to study how light behaves in the harsh environment right at the edge of a black hole's grip, without needing to wait for a rare, extremely bright quasar to study instead. A pattern that kept showing up later. NGC 3147 was an early example of a theme that would repeat again and again in black hole research over the following years. A black hole would appear to defy the accepted rules. Headlines would follow, and then careful follow-up work would reveal a more complicated but still fascinating reality underneath the initial shock. Later studies of black holes in the very early universe, made possible by newer telescopes with even sharper vision, ran into similar surprises involving black holes that seemed to grow too fast or glow in ways that did not match their size. In more than one case, the extreme numbers first reported turned out to be shaped by factors researchers had not fully accounted for, whether that meant dust clouding the view or gas distorting how bright an object appeared. Each time, the underlying discovery still mattered, even after the most extreme version of the story was corrected. NGC 3147 fits neatly into that same pattern. A black hole that should have been the most boring, predictable object in its galaxy turned out to be hiding a structure that forced astronomers to rewrite their assumptions about where thin disks can and cannot form. The universe kept finding new ways to remind researchers that its rules have far more exceptions than any single model can capture, and that the objects looking the calmest on paper sometimes hide the strangest secrets once a sharp enough instrument gets pointed at them. The Milky Way has the same problem. NGC 3147 was not an isolated oddity sitting far away from anything familiar. Our own galaxy has a supermassive black hole at its center called Sagittarius A, and it is famous among astronomers for being almost embarrassingly quiet. It weighs around 4 million times the mass of the Sun, yet it produces only a tiny fraction of the light theory says it could if it were feeding at full capacity. For decades, scientists explained this quiet behavior using the same basic idea that the NGC 3147 team was trying to confirm: the notion that starved black holes lose their neat, thin disks and settle into thick, puffed up clouds instead. Sagittarius A fits that description reasonably well based on current data, which is part of why the result from NGC 3147 stood out so sharply. Here was a black hole on a similar meager diet, yet it was hiding a thin, fast-spinning disk that theory said belonged only to much hungrier objects. That contrast gave astronomers a genuine puzzle to chase. If two quiet black holes on similar diets can end up with completely different structures around them, brightness alone cannot be the deciding factor. Something else, whether it involves the exact rate of feeding, the angle of the surrounding gas, or the history of how each black hole grew, has to be shaping whether a thin disk survives or collapses into a thick cloud. Answering that question meant looking at more quiet black holes across more galaxies, rather than assuming one tidy rule applied to all of them equally. Why this kind of detail matters so much. It might seem like a small technical detail whether the gas near a black hole forms a thin disk or a thick cloud, but that shape carries real consequences for how astronomers understand galaxies as a whole. Supermassive black holes and their host galaxies appear to grow together over billions of years, and the structure of the material feeding a black hole affects how much energy gets released back into the surrounding galaxy. A thick, puffed up cloud tends to release energy more gently and over a wider area, while a thin, fast-spinning disk concentrates that energy into a smaller, more intense region. Getting this detail wrong in a model does not just affect one black hole on paper. It can throw off predictions about how galaxies regulate their own star formation, since the energy pouring out of a central black hole is one of the forces that can either encourage or shut down the birth of new stars nearby. That is part of why a discovery like the one in NGC 3147 carries weight far beyond a single spiral galaxy 130 million light years away. Every model that assumes a clean, predictable relationship between a black hole's brightness and the shape of its surrounding disk now has to account for at least one clear exception, backed by some of the sharpest data Hubble has ever produced on a black hole this faint. What it all adds up to: put everything together, and the story of NGC 3147 becomes a reminder of how much is still unknown about the object sitting at the center of nearly every galaxy in the universe. A black hole chosen specifically because it should not have a certain kind of disk ended up having exactly that disk, spinning so fast that it bent light in ways predicted by Einstein a century earlier. None of this happened by accident or guesswork. Every measurement came from careful analysis of real Hubble data, cross-checked by an international team of astronomers from Italy, Israel, Spain, and the United States, and published in a peer-reviewed scientific journal for other researchers to examine and challenge. A telescope launched decades ago to study galaxies far beyond our own ended up. Rewriting a basic rule about how black holes should behave right in our cosmic backyard. Black holes were supposed to follow a simple, brightness-based rulebook that scientists had trusted for years. NGC 3147 showed that the real universe is stranger, messier, and far more willing to break its own rules than anyone had planned for. If this video gave you something, subscribing takes 3 seconds, and it helps us keep making content like this.